Welcome to the third Harvard Data Science Initiative Bias Square seminar, featuring Professor Cynthia Rudin of Duke University. I'm Francesca Dominici, and together with David Parks, I'm one of the two Harvard Data Science Initiative faculty co-director. This series is part of our largest Bias Square program, which we launched in September of this year as part of our efforts to address the structures in our field that reinforce bias and systemic racism. The monthly seminars in this flagship series complement a newly established research fund and an expanded graduate fellowship program, and will feature the leading scholars in our field who are working to shed light on different types of bias through the use of data science, as well as speakers who raise concerns around problems with data, algorithm, and data science methodology. Before getting to today's talk, I want to mention that our industry seminar series will be hosting the City of San Jose Chief Data Officer, Christine Kung, on February 18 to talk about data equity. Now, it is my honor to introduce Cynthia, a friend and a colleague. Cynthia is a professor of computer science, electrical and computer engineer, and statistical science at Duke University, and directs the Prediction Analysis Lab, whose main focus is in interpretable machine learning. She's also an associate director of the Statistical and Applied Mathematical Science Institute, SAMSI. Previously, Cynthia held positions at MIT, Columbia, and NYU. She holds an undergraduate degree from the University of Buffalo and a PhD from Princeton University. She is a three-time winner of the Inform's Innovative Applications in Analytics Award, was named as one of the top 40 under 40 by Poets and Quants in 2015, and was named by Business Insider as one of the 12 most impressive professors at MIT in 2015. As a reminder, you might pose your question from Cynthia throughout her talk using the Q&A functionality in Zoom at the bottom of the screen. And at the end of the talk, we will invite one of our Harvard Data Science Initiative postdoctoral fellow, Hannah Correa, to moderate your question. Welcome. Thank you for joining us. And I'm turning to you, Cynthia.
Thank you, Francesca. All right. Okay, so I want to start with a question. Can a typographical error lead to years of extra prison time? Right? This should never happen, right? Typos making decisions? That's crazy, right? Who's making decisions here, a judge or a typo? Would it be fair if a typo made a decision for someone? But it happens all the time. So I'm going to give you an example here. This is an article from the New York Times about the COMPAS model, which I'm sure a lot of you have heard of. And it's a case where a person was denied parole because his COMPAS score was miscalculated. So for those of you who don't know, COMPAS is a proprietary model. It's a black box. Nobody knows what it's calculating exactly. And it's used throughout the criminal justice system in the United States. And it's used to predict whether somebody is likely to commit a crime in the future, commit another crime in the future. Yeah, so here it was miscalculated. And what happened was he actually went to this was a guy who was in prison since he was a teenager. He was a model prisoner. He comes up for parole. His parole is denied. And he leaves, right? And then he looks at his score sheet and compares it to someone else's and realized that there was a typographical error in his criminal history features. Okay, so a black box model is a formula that's either too complicated for any human to understand or it's proprietary, like the COMPAS score. And in contrast, an interpretable machine learning model is constrained. It obeys a domain-specific set of constraints so that humans can better understand it. Now, I want to give you just a more technical definition here, which is that interpretable machine learning models constrained in model form so that it's either useful to someone or obeys some kind of structural knowledge of the domain, such as monotonicity, causality, generative constraints, additivity, or some kind of physical constraints that come from domain knowledge. Now, there's a spectrum between models that are kind of just loosely constrained, like they're forced to be increasing along one variable, for instance, to models that are very tightly constrained, where you can really understand how the variables work together to jointly form the prediction. Now, why do you need interpretable machine learning models? Well, you need them for high-stakes decisions or troubleshooting. And high-stakes decisions are basically anything you really don't want to go wrong. Things like criminal justice decisions, credit scoring, air pollution questions, airplane maintenance, lots and lots of healthcare applications, anything that's, anything that you really don't want to go wrong. So what happens when we use a black box in practice? Well, bad things. So here's an example where it's an article about the California wildfires in 2018. So if you lived in California during that time, you might have been using Google's daily air quality predictions to determine whether it was safe to go outside. And you might have seen Google's predictions that air quality was fine on days where people were also seeing a layer of ash on their cars. Because during the wildfires, Google replaced the Environmental Protection Agency's Trustworthy Air Quality Index with a proprietary machine learning model from this company, Breezometer, which claimed to be more accurate. But clearly the proprietary model was not doing what it was supposed to, and it put a lot of people in danger. Another thing that could happen to you is you could receive worse healthcare because of your race. And so this is a very popular article that pointed out that a hospital was ranking patients to get additional attention, and white people got higher rankings even if they were not as sick. And the reason is because the algorithms were using cost information to predict who should be given care. And the Black patients were receiving lower cost healthcare. And so the algorithm thought that they were less sick and didn't recommend additional care for them. And if the model wasn't proprietary, then we might have been able to figure that out fairly easily. And this is just the tip of the iceberg because, I've given you a few things that have gone wrong using black box models, but there's a tremendous amount more that could go wrong. And probably many things have gone wrong that were hidden, and so I don't know about them. And now people are starting to use machine learning for medical decision-making and loan decisions and self-driving cars and all manner of other things that you really don't want to go wrong. And some people love their black boxes, like they argue fiercely that they need them. Anyway, so I want to go back to this example over here and just question why we might need a model like Compass, right? You'd think that because it's a black box, it's proprietary, it's been developed over years and years, that it was more accurate. But thanks to ProPublica, who provided a lot of Compass scores for people from Florida, we can actually determine how accurate Compass is. And when the ProPublica article came out a few years ago, we took the data from that article and we ran our latest machine learning method on that data to see how accurate Compass was compared to a machine learning method on the data. Okay, now remember, Compass uses, say, 137 factors, up to 137 factors it can use because it collects a huge amount of information from people. Whereas the data that was made available by ProPublica was only like a few factors, right? So the question is, how well can we do with our latest machine learning method from the lab with only the few factors that were made available by ProPublica? So we compared Compass to our latest machine learning method. At the time, it's called Corals, which is just certifiably optimal rule lists. So this is an optimal decision tree method. And we sent the ProPublica data into Corals to try to predict criminal recidivism. And the machine learning model we got out was so tiny that it fits into the corner of a PowerPoint slide. And the model is right here. So it says, if you're young and you're male, predict that you'll be arrested within 2 years of your Compass score calculation. Else, if you're a little bit older and you have a couple of prior offenses, predict arrest within 2 years of that Compass score calculation. Also, if you have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and we were just thinking, there is no way that this model can be as accurate as Compass, right? No possible way. But the surprising thing is that we were wrong. So this is accuracy scores of compass and corals across 10 folds of cross-validation. So the different colors are different folds of the data. And what you can see is they're both about equally accurate. And not only that, but it didn't really matter which machine learning method we tried. We tried a lot of them, and they were all about equally accurate. And some of these are, like I said, black boxes, like Compass is a black box, boosted decision trees, random forests, support vector machines with radial basis function kernels, right? These are models you can't fit on a PowerPoint slide or in your head in any way. And on the other extreme is corals, whose whole model is right there. And now there was a huge debate about algorithmic fairness of Compass, but the truth is that we just don't seem to need Compass at all. So, why are we still using it? Now, so far, I just talked about interpretability, interpretable models, and how they, didn't lose accuracy in this case, and it turns out in other cases as well. Now, explainability is very different than interpretability. Now, interpretable machine learning is where you use a model that's not a black box. In explainable machine learning, that's where you take a black box, you start with a black box, and you try to explain it afterward. So you do a post hoc analysis on the black box. So in other words, you start with a black box, and you either create a model that approximates it, or you compute derivatives of it, or you try to visualize what part of the input the model is paying attention to, or compute, you basically just try to make an excuse for why the black box model is doing what it's supposed to do. You're basically trying to justify the existence here of the black box model by trying to explain it rather than replace it. Now, I want to make the important point that interpretable modeling is not the same as explaining a black box model. There's a very big chasm between these things, and even people in the field of machine learning don't get it. So let me give you a couple of reasons why these things are different, and most people don't really understand this. So let me give you a few reasons. Okay, the first is called double trouble. So when you're using a black box and explaining it, that forces you to rely on two models instead of one, the black box and the explanation. And those models have to disagree with each other. If they didn't disagree with each other, you could simply throw out the black box and just keep the explanation, because the explanation is an inherently interpretable model that's just as accurate as the black box. So they have to disagree with each other. So then how often do they disagree with each other? Well, let's say they agree with each other 90% of the time. So most people are happy with that. But the problem with the 90% agreement is that it's wrong 10% of the time, which means 10% of the time you can't trust the explanation, which means you can't trust the black box. So it just leaves you kind of back in the situation where you're trusting a black box, or stuck trusting a black box. Also, typographical errors are really a problem when inputting data into black box models, as I showed you with Compass. Think about the number of people who've been subjected to typographical errors from even this one particular model. And I think the most important argument is that if you can produce an accurate interpretable model, why should you be explaining a black box? Is the explanation an excuse for improper data analysis? Are we using black boxes when we don't need to? Now, I want to also make the point that terminology is important. When you say the word explanation, that is not the same as approximation, right? Approximations are not explanations. They can get variable importance wrong. So I'll give you an example here where f of x is my black box. Okay, so here's my black box there. It's maybe some super complicated function in higher dimensions or whatever. And I approximate it with a linear model that's locally, reasonable approximation, okay? So these things are approximately equal to each other. Now it turns out that the explanation depends on age, number of priors, and race. So then you might think to conclude that the black box depends on race, but it turns out that the black box depends only on age and number of priors, okay? So, you know, particularly for proprietary models, you know, if you try to do this kind of approximation and without considering variable importance, your explanations can get really all messed up. And you could say that this would never happen, but it actually might happen. And it actually did happen. And in particular, it happened with compass. So the ProPublica article, this is exactly the technical error that they made. They took compass and approximated it and claimed that the important variables for the approximation were also important variables for compass. So I'm just going to put up the article here. And then I want to go through what they actually did. So they did exactly this. They did exactly what I was talking about. They approximated compass with a linear approximation and then claimed that the important variables of the approximation were important to compass. So let me give you more detail. So they started by showing that the false positive rate and false negative rate of compass varied by race. And then they suggested that that might not actually be a good comparison because the populations were actually different. They said we should condition on age and number of priors and re-examine because it might be that the false positive and false negative rates were controlled mostly by age and number of priors. So they said, we'll take those into account and then we'll try again to figure out whether compass depends on race. So after conditioning on age and number of priors, they still found a linear approximation to compass with a low p-value for the race covariate. So in other words, they found a linear model that depended on age, number of priors, and race. And then they concluded that compass must then depend on race. Now, the problem here, of course, is that we don't think compass is actually a linear model. And so their conclusion doesn't follow from their logic, okay? So let me show you why ProPublica's assumption was particularly bad. Now, as I mentioned, ProPublica provided data. They actually provided data to check their analysis. And so we did. So we scatter plotted the compass score versus age. So each dot on this plot is a person whose compass score was calculated. And I don't know if you can see, but there's a pretty clear, like, just a pretty clear curve here. It's kind of dramatic, actually. Like you wouldn't really find a 60-year-old with a, or sorry, you wouldn't really find a 20-year-old with this compass score of like -4, right? You find a 60-year-old with that, but not a 20-year-old. And there are a few outliers that sort of don't follow this, but this curve here, it holds for almost everyone in the data set that everybody is above this curve. So this sort of sharp cutoff of compass scores for each age. And we think that these are possibly the minimum compass scores for each age. So if you are this age, the minimum compass score you can get might be that value right there. So these, obviously there could be a few typos that disagree with us, but even right on these values, there were like many, many, many people that had exactly the same compass score there. So overall, not pointing to a linear function of age here. And it really looks like compass depends heavily on age, particularly for like younger people. And so if ProPublica messed up the dependence on age, that could definitely mess up their analysis. So we were wondering like what compass actually, whether it actually does depend on race. And so we said, fine, we'll take that function of age and subtract it out. So we'll take compass minus that function of age, because if that function of age is, that's some dependence on age, right? So let's take it out and let's see if the remainder depends on race. Now, what we found is that it really doesn't seem to. And we concluded that after running machine learning methods with and without race to see if they needed race to predict compass well. And they perform very similarly. And these are very flexible models. And so we really weren't seeing that compass depended on race other than through age and criminal history, which are correlated with race. And so kind of wonder then, how did you're probably wondering about these pairs of people that ProPublica talked about in their article and what happened there, right? These examples were like key evidence on how Compass depends on race, right? Because the white person had a longer criminal history and a lower Compass score. And the thing is, if you look at these two people, the black person is much younger than the white person. So if Compass depends heavily on age, that could totally explain how this happened, right? Rudin Prater, he's old, so he doesn't get the age points. And I'm not saying that I agree with Compass. I'm not saying that this is a good idea, but if ProPublica had compared two people of the same age, it would be much more convincing that Compass depends on race in addition to the strong dependence on age. So I think it's possible that Compass doesn't depend on race other than through its dependence on age and criminal history. But I think Compass has a much worse problem that ProPublica completely missed. All right, so Compass has up to 137 factors. They're all entered by hand for each survey. If there's even a 1% error rate on that data entry, then there's a 75% chance of at least one typo on a survey. And humans are really not very good at inputting data reliably, which is what caused, the issue with Glenn Rodriguez. And this is really a serious disadvantage to complicated or proprietary models. They're difficult to check in real time. And there's Glenn Rodriguez again. Yeah, it's exactly the same problem that I talked about at the very beginning. Now, we were looking at the Florida data to try to figure out how often these typos might happen, and we found some really strange inconsistencies in the data. And this is a table of some of these inconsistencies. So here, these are people who have the lowest Compass violence decile score right here. And then this is their number of prior arrests and charges. And these are just a sampling of some of their prior charges. So I mean, these are things like attempted murder in the first degree, resist, obstruct officer with violence, aggravated battery with a deadly weapon, robbery with a deadly weapon. So these are people who have the lowest possible Compass violence decile score. And I really can't make heads or tails of how to reconcile the Compass scores with this data, other than that there's some kind of data issue, like data, entry issue of some kind. I'm only showing you the tip of the iceberg. There's much more to this table. These are people with Compass scores of 2 and 3. And then here are their charges. I mean, look at the number of charges and number of arrests here. It's like unbelievable. Anyway, as we were doing this, we even think we found a typographical error in the documentation from Compass. So this is the formula that they've actually written for that violence Compass score. It actually says it's linear, but we actually think that there's a corrected version which has some extra functions in it that they sort of inadvertently left out. So we've basically been finding typographical errors everywhere, which is another really strong reason to want to use interpretable models for high stakes decisions. You don't want to make a mistake. Anyway, so I want to go back to this idea of interpretability versus explainability. And I want to point out that scientific evidence really doesn't support the interpretability accuracy trade-off in machine learning. Now, this is an image from the DARPA Explainable AI BAA. And on one axis, they have learning performance, and on the other, explanation effectiveness. And the plot is supposed to illustrate an inverse relationship whereby you would get worse explanations for better accuracy, right? Like that you have to sacrifice something in explanation power to gain more accuracy. And there's some major issues with this figure. The first one is that the figure doesn't seem to correspond to any real problem. This is just sort of matheism. It looks like someone drew it. It's like Trump with the Sharpie or something. Like it just doesn't correspond to any real problem. And then also, it looks like someone, it seems like it's supposed to illustrate someone running a bunch of different machine learning algorithms on a static data set with a fixed evaluation metric. But that's not how we do data science. The way we do data science is that we run, we process the data, then we run our algorithms, and then we look at the result and interpret the result. And that tells us how to refine our data set and our evaluation metric. It's a cycle. And interpretability improves that overall cycle. It actually doesn't hurt it. So this doesn't really convey that aspect of the value of interpretability. And then also, even if you were running many different algorithms on a static data set, you wouldn't find a trade-off like this. I just showed you an example where we ran several different algorithms on the Florida COMPAS data, and it was flat, right? The accuracy really didn't change as we gained substantial amount of interpretability. And even for even for deep learning and computer vision, it's pretty flat. And I'm going to show you some examples later. We don't really lose accuracy, even in the deepest of the problems where the deepest of the deep neural networks are the king. Even in those computer vision problems, we still find it's fairly flat. Okay, then, I kind of wondered, well, are they talking about explaining black boxes or designing inherently interpretable models? And as it turned out, they were only talking about explaining black boxes. Now, when you explain a black box, you might suffer some approximation error, like your approximation might not exactly mimic the black box, and then you might actually suffer some error. But when you're trying to create inherently interpretable models, there's enough freedom in the data that you can generally construct an interpretable model without losing any accuracy. Okay, so I was watching the world kind of lean more and more toward explaining black boxes, and I finally decided to do something about it. So I wrote a workshop paper called Please Stop Explaining. It was called Please Stop Explaining Black Box Models for High Stakes Decisions and Use Interpretable Models instead. But when I submitted it, the editors made me take out the please. So it's a little bit more commanding, right? But anyway, so in this paper, I gave a lot of reasons, and I just want to tell you some of them, which are essentially the ones I've already told you. Typographical errors cause problems for high stakes decisions with black boxes, no matter how you explain them. Black boxes still force you to trust the data set. And I have never met a large data set that didn't have some serious error or serious problem with it. The issue with double trouble that I talked to you about, that if you're explaining black boxes, you have two models that you have to troubleshoot instead of one. They have to disagree with each other. I've also told you about this issue with the terminology of approximation versus explanation. If you approximate a black box, you can't assume that the variables that are important in the approximation are the same as those that are used in the black box. And so that's the problem exactly the problem that ProPublica had with their analysis. And then finally, the most important, so for the ProPublica article, right, you kind of wonder if Compass was actually public, would they have written the same article, or perhaps they would have written an entirely different article, right? Maybe instead of saying this model depends on race in addition to age and criminal history, maybe they would have written something quite a bit different about the reasons why we shouldn't have black box models. Anyway, if you can produce an interpretable model, why should you explain a black box, right? Well, why do we need Compass? Why do we need these models that are proprietary? Do you really want to extend the authority of the black box by trying to explain it rather than to replace it? Now, I want to provide a little bit more nuance on these assertions that we don't seem to be losing accuracy when we gain interpretability. There's a kind of a spectrum of different problems in machine learning. And on one hand are problems with tabular data, and then the other with raw data. So tabular data are kind of like what I get in these medical problems that I always end up with. I don't know why I somehow always get tabular data, but unless I've actually sought out raw data, I tended to get tabular data in my problems. And these are data that look kind of like this. It's like real values or categorical values, and each of them are inherently meaningful and predict the outcome. Whereas with raw data, that's where you have your features are individual pixels or bits of a time series. or words in a large document, right? Knowing one pixel, that's not really going to tell you anything about what the image is actually about. And so for raw data, the only tools that seem to be really working right now are neural networks. That doesn't mean that's going to be the way it always is, but that's the way it is right now. And for these problems also, you need to think carefully about what constitutes interpretability. Again, interpretability is a set of constraints. So you have to create the constraints to actually match the problem. And in computer vision, it's not clear what that actually means, right? Whereas for tabular data, it's a very, very different story, where with minor preprocessing on the data set, all the methods tend to have very similar performance, just like I showed you with the COMPAS data set. So what that means is that it opens the door for very sparse models like decision trees, like the Quarles model, or scoring systems where you have points for things and you add them up. Those very sparse models actually tend to do as well as neural networks or anything else for tabular data. So for tabular data, and in particular for many different recidivism problems, I've worked on recidivism for years, and for all of the recidivism problems I've worked on, we were able to create interpretable models that were just as accurate as the best black box models. Now, I say this, right? And also for neural networks, I'll show you in a minute that as long as you create the interpretability constraints carefully, you actually won't lose accuracy over the black boxes. So I'm saying we can create interpretable deep neural networks, and I'll show you kind of how that goes in a minute. Now, I say this, and people immediately question this, right? They say, no, it's not possible, you know? These things must lose accuracy because they're constrained. You'd think that a black box is more accurate, but it's not always the case, and in fact, it's not even usually the case. And the key, though, is being able to choose a good definition of interpretability that matches the domain. And if you do that correctly, the interpretability can actually help with accuracy because you can now troubleshoot. You can see what you're doing, and then you can troubleshoot it. So my lab works on a number of different interpretable machine learning problems. And I'll just tell you a little bit about some of the long-term projects that we have going on in the lab. Optimal sparse decision trees we've been working on for many years. And this is an NP-hard problem with no polynomial time approximation, but we can still solve it fairly efficiently and get fairly accurate decision trees that are very, very sparse. Scoring systems, which are sparse linear models with integer coefficients. Interpretable deep neural networks for computer vision. Data visualization and dimension reduction. Matching for causal inference, where we try to match treatment and control units together to be able to estimate conditional average treatment effects. And then we've also been trying to understand the set of good models and the importance of variables. So I want to, you're probably kind of staring at this going, interpretable neural networks for computer vision, what is that? What does that actually mean? So what I want to do is, tell you a little bit about that. So I'll give you one example. So this is a recent paper that we've rewritten. It's called Concept Whitening. And concept whitening is designed for neural disentanglement. And the goal is to whiten the latent space, like white noise, where the method normalizes and aligns the latent space so that concepts are on the axes, so that the axes of a neural network's latent space are actually meaningful. Okay, so convolutional neural networks, they are not naturally disentangled. You would not naturally find that all the information about airplanes goes through one neuron and the information about cars goes through one neuron. Like, this is not what a normal neural network does, because you're not telling it to do that. And so it spreads the information all over the network. Now, I want to take a standard black box convolutional neural network and think about the latent space of a particular layer in the network called a batch norm layer, okay? So I have this layer here. There's neurons 1, 2, 3, 4, 5. This is neuron 1 and neuron 2. And then I want to take a vector of the activations of each concept, okay? So when you send an image into that network, you know what's in the image, and then you can plot which neurons are activated, okay? So you take that image, send it through the network, and then you find that, say for this image over here, both neuron 1 and neuron 2 are highly activated. They get very excited when this particular image goes through. But when this other image comes through, well, in this case, in fact, neuron 1 is excited, neuron 2 less so, okay? All right, so now what people have been trying to do is explain the latent space of a neural network by creating these vectors that point to different concepts. So they're saying, okay, in this direction is this concept, in this direction is that concept. Like this is airplanes and this is cars. The problem with this method is that it doesn't truly explain what's going on in the latent space of the network. First of all, airplanes might be all over the latent space. And so when you draw that vector, you think airplanes are in that direction, but they're actually all over the place. Also, you could have problems where two concepts have vectors in the same direction, even though they're actually very different from each other. It's just that their concepts are going in the same direction. So it's not really clear that this idea of creating these concept vectors is actually meaningful or doing anything. And it's really not telling you what the network is actually doing. Okay, so yeah, these vectors, they are not naturally orthonormal. So what we decided to do was replace the batch norm layer with a module that we call concept whitening. And concept whitening, when a concept whitening module is added to a CNN, the latent space is whitened, so it's decorrelated and normalized. And the axes of the latent space are aligned with the concepts that we're actually interested in. There we go. So yeah, so now you have neuron 1 being like the airplane neuron, and neuron 2 being like the car neuron. And so the only time that neuron 1 would get activated is if it thought that there was something resembling airplane. And so doing this can really tell you kind of how much airplane, how much car the network is using to make its final decision about what's actually in the image. All right, so when concept whitening is added to different layers, it does different things. So I'm going to show you what happens if you add a CW module to the second layer of a network. Now, in the second layer of a neural network, there's not much processing that can go before that because it's only 2 layers deep. So it just can create very primitive concepts. Now, the network here is trying to figure out what the scene is, whether it's a bedroom or an airfield or, you know, what kind of room it is, kitchen or something like that. Now, it's going to tell us what information about airplane. It's going to show us the images that are the most highly activated on the airplane axis on the second layer. Okay, so interestingly, none of these are airplanes. They're all kind of sea creatures. But it's telling us what the network is doing at that second layer. You know, where does it get excited about things that look like airplanes? And as you can see, it created a primitive notion of what airplane is, which is a blue background with kind of a gray object in the middle, of a gray or white object in the middle. So it kind of created an abstract notion of what an airplane is, and sent all information about airplane through that particular node in the network. And then it created an abstract concept of bed, which was kind of like a busy texture. Actually, it's more like colors. Like this is more like textures. The person node. The bed node is more like warm colors. It's like pinks and oranges and reds. So in earlier layers, basically all the network is capable of doing is funneling. You know, the activation is basically mostly on color and texture information that are related to the concepts. Whereas in later layers, it actually has enough expressive power to detect what an airplane is on its way to detecting airfield. And so it really does detect airplanes kind of along its way to detect airfield. And so these are the most activated concepts along the airplane axis. And then these are the most activated, images on the airplane axis, on the bed axis, and the person axis. Great, so how does this help us? Well, now, it's actually really interesting to kind of look at how the network processes an image as it goes through the layers. So this is the image I want to look at. This image is interesting because it has neither a bed nor an airplane in it, and it has bright colors, which is what you would expect from a bed at earlier layers. But it also has a sky, which is related to airplanes. So what does the network do? Well, very early on, it thinks it's activating very highly on the bed axis because of those warm colors. And then as the network becomes more sophisticated, kind of as the layers go deeper, it starts to realize that maybe this is not a bed. And maybe actually because of that blue sky, maybe it looks more like an airplane. So then it's highly activating on the airplane axis. And it's interesting to kind of see it move around as it goes through the different layers. Now it really thinks it's an airplane. It's like, I see clouds, I know what it is now. And then finally, it realizes that it is really not a bed. It could still potentially be an airplane, but it's really not a bed. Okay, so the advantages of CW over the batch norm is that we've done extensive experiments and haven't found any sacrifice in accuracy to really make the latent space shape nicely. So now we understand what the axes are of the latent space. That's something we couldn't do before in a regular neural network. Yeah, the accuracy is on par with standard CNNs. You just take your favorite black box, take the batch norm layer, replace it with a CW layer, run it for one more epoch, and off you go. Yeah, it's really easy to use. You just if you have your pre-trained model, pre-trained black box, then you just, again, you swap out that layer, replace it, run for one more epoch through the one full iteration through all the training data, and that's it. And it disentangles the latent space. And maybe, if you wanted to, you could try to put all the information about race or something through one part of the network if you wanted to kind of disentangle the network's race information from other information if you're looking at images of people. Or even, you can use it for non-images of people if you want to. You can use it for other types of data as well. All right, so just to summarize, predictive models are really everywhere. They're in criminal justice, they're used in air pollution, as I showed, allocation of health services, medical treatment, recommender systems, self-driving cars. Don't we want to be able to troubleshoot them? Don't we want to be able to detect if they're biased in a harmful way? Don't we want to be able to ensure that a typo didn't make a decision for us? Don't we want to be able to use these models in high-stakes decisions? Don't we want to understand what these models are even doing? And yeah, that's the whole reason for this talk. Thank you.
Well, thank you, Cynthia. That was just a wonderful, beautiful talk, and we really appreciated both the methodology that you were able to cover in a short time, but also the content that you covered in regard to recidivism as well. And this is exactly the type of work that we've been wanting to feature in the seminar series. So thank you for presenting. It's my honor now to introduce Hannah Carrera, who's a postdoctoral fellow in the Data Science Initiative. Hannah's a postdoc also in the Department of Biostatistics in the Chan School. And she does work related to causal inference, and she uses it to study ecosystems and ecology. Hannah, are you here? Are you ready to moderate questions? Great.
Yes, thank you, Kevin, David. Cynthia, thank you so much for such an excellent talk. It was really interesting. And we've got lots of great questions in the chat. So let's see.
Shall I start answering them, or do you want to?
We put them in order of your talk if you want to sort of go from the top. could you give some examples of black box models for our listeners?
Well, I did give a few in the talk. So I gave the example of Compass, which is proprietary, and then the model from the company that does the air quality breathometer. That's another proprietary model. There's that model that's used by the healthcare company that was predicting costs as a proxy for need of care. So those are examples of black box models because they're proprietary. Also, I gave models that were black box because they're too complicated for any human to understand. So things like boosted decision trees and random forests and support vector machines with radial basis function kernels and neural networks that aren't constrained to be interpretable. Yeah.
Another person asked, what is the violent decile score of Compass is supposed to predict? So I think you mentioned that it basically predicts their likelihood of committing another crime. Is that correct?
Yeah, violent recidivism. Yeah, violent crime. That's right.
Where do the answers to a Compass-like survey come from? Do they interview the detainee or just from public records or?
No, there's a survey, there's a form, and you can actually download copies of like sample Compass forms. That the forms change over the years, but you can get a copy of the form. And they ask them different questions in many, many different categories. And it's unclear which of those questions exactly are used for which Compass score. It's possible that the violence score and the general Compass score are actually fairly, like that they don't have too many variables, but since we don't actually have access to the formulas, we don't actually know that. It's just, there's this huge, it's like a huge survey, tons of questions about employment and school and, criminal history and all that stuff. And then something is calculated from it.
I see. Okay. So you talked a lot about typos and errors and entries. If they're so impactful, what processes do you suggest that companies and agencies implement to eliminate or reduce errors? And also related, does using an interpretable or explainable model prevent input typos, and if so, how?
So there's no real way to completely prevent a human from making a mistake on a data entry issue. But if they had been using something like the Arnold PSA or a much simpler model, which is only a few variables, like say 7 variables, and they actually let the person look at it to see whether there was a typographical error in it, then it would have been a lot easier to make sure that there wasn't an error. So in other words, like the PSA, I think it has only 7 questions on it, and the formula is public, and then the people who are subject to the model actually get to look at the model and the inputs to it. Whereas with Compass, the people who are subject to it, they would have to look over this sheet of 137 factors to check for it. It's just much more error prone. It's a larger possibility for errors.
So error prone because of its complexity, and also error prone because the fact that the person looking back at it cannot handle all the information that's being put into this model.
Yeah, and they don't know what the model's actually computing. Because like if you get a Compass score that's really bad and you knew what the formula was, you'd be like, oh, what was the most important factor? Oh, criminal history. Well, I don't have any criminal history.
Yeah. Okay. So in studying FPR and NRR, did ProPublica have access to the scores coming out of the Compass system?
Yeah, that's what they posted. They actually had the scores. Yeah.
And if they did, what did they need to fit a model to understand disparate errors?
So again, the problem was they didn't take into account the confounding, right? That you can say, okay, there are disparate errors, which there were, but the populations were different. Because of systemic racism in society, the Black people in the database were younger and had more priors. And so, well, then you have to kind of figure out how to disentangle these things. And you can't just say, oh, look, it depends on race. It's like, no, it depends on race through age and criminal history. Now, if you knew that the model, maybe it only depends on age and criminal history. If you knew that, would you still write a paper that says that Compass depends on race explicitly? Like, why didn't they write the article on the PSA, right? The PSA depends on age and criminal history too, but yet they didn't write an article on that. And the reason they wrote the article on Compass because it was proprietary, and so they couldn't understand it, because it wasn't transparent, because it wasn't interpretable like the PSA.
Yeah.
So I think the whole, the whole reason for that article was honestly lack of interpretability, lack of understanding.
Yeah. So do your simple interpretable machine learning model for recidivism provide comparable accuracy, for example, AUC accuracy for different groups? And how does it compare along the dimension with Compass?
It's almost exactly the same as Compass, and we did that analysis and put it in the paper. Yeah.
Okay. Have the owners of the Compass algorithm given any response to your analyses or the ProPublica analyses? And what did they say?
They did. Actually, the Harvard Data Science Review published the Age of Unfairness paper that I was talking about that kind of went over where ProPublica went wrong in their analysis. And they actually got Compass to respond. And they actually wrote a nice response to our article. Obviously, they weren't happy that we found the typos in their documentation. And they weren't happy that we were kind of potentially finding out what's little bits of their secret formula, but they sort of admitted that the typo was real.
Interesting.
You should check out. It's pretty funny.
Interesting. Did they suggest any sort of, that they know they need to improve, or that they'd like to see more open source things or anything like that? I mean,
they did.
They did. Wow.
Yeah. So the one thing, there was two things that were really interesting about their response. So one of them was that they said that the model could be viewed by the right decision makers, and yet the people who are actually subjected to the model cannot see it. So even if the judges, even if the parole board could see the model, the person subjected to it cannot see it. So it's and they sort of neglected to mention that, which I thought was interesting. But they also said they were working toward trying to make their model to put their model under, I think, patent or something like that, which I thought was really interesting. It's like, maybe you are going to make the model public because you realize that our criticisms are real. I mean, when they responded to ProPublica and said to ProPublica, "Hey, your article's wrong," like they actually had something there, right? They were actually maybe correct, right? But it was hard for them to say that about our article.
Yeah. Interesting. Somebody had some thoughts on systemic issues and how they may be playing out here. So race may not be a prioritized explanatory variable, but indirect correlation with race via prior record. Evidence that POC are charged with higher level offenses or other things like that. Thinking of how high dimensional models are touted as capturing, quote, underlying confounding, could that be reflecting structural isms?
Yeah, so exactly. And I said that directly in a few minutes ago. Yeah, I said, look, age and criminal history, because of systemic racism, are correlated with race.
Yeah.
And that's something people need to deal with. Like, you have to decide, is it fair to place age in a model for criminal recidivism?
Yeah.
Younger people are more likely to commit crimes, but because of systemic racism, you're arresting people at younger ages who are Black.
Yep.
But so people need to deal with that question. Is it okay to put age in a criminal recidivism model? That's a different question than than the ones we were asking before, right?
Yes.
The interpretability allows you to dissect it down to the correct question.
Yeah. Because at least you can see what's going on in the models then, and understand how important they are in the models.
Yeah, and you try to minimize it by, changing what you're predicting. So maybe we shouldn't be prioritizing lower offenses, like lesser offenses.
Yeah, absolutely.
We should be predicting only crimes that people have been convicted of, and not crimes that people have been convicted of. And so we made a point of that in our latest paper on recidivism, where we're evaluating fairness and interpretability.
Yeah. And I guess, having more interpretable models means that you can then create a set of best practices for what should be included in these kinds of models and what should be excluded for that reason.
Yeah, and it just really depends on how the models are going to be used. I mean, you don't want, there's certain types of things where, like, you don't really want to be using predictive models for sentencing, for instance, because sentencing, you should be punished for the crime that you committed, not the crime that you're going to commit.
Yeah.
But, or at least it should not factor like heavily, like the prediction shouldn't factor heavily in the sentence. And we don't do that in our society. We punish people for what they actually, the crime they actually committed in general. But on the other hand, for things like bail or parole, like, yeah, you might need to actually take this into account, because if somebody has a really long criminal history, you don't want to just release them on bail. It just seems dangerous for the public, right?
Sure. So let's go on to your concept whitening. So in regards to CW, how scalable is this beyond a few hidden layers? How does the running time compare between the CW and, say, a more typical approach?
Okay, so for the running time, it's really not that bad at all. You just run it for one additional epoch. You can put CW in any layer. We haven't been able to put it in like all the layers at once, but it seems to be, it seems to operate just fine. You should check out the paper if you're interested in trying it out. We have code available too.
Yes, I saw that. Is there an extent to which hierarchies, complexity in feature learning in neural networks confound concept whitening? For example, images are too similar to be distinguished clearly on concept axes. For an example, planes are very different from bedrooms, from people. What about, say, tissue types?
Yeah, so that's actually something we recommended trying in our future works. We actually think that's an important topic for the future. So what we think we want to do is, instead of trying to put each concept on its own axis, you could have some axes that are allowed to be correlated with each other, but then force other axes not to be correlated with each other. So for instance, you could try to create this kind of block diagonal structure where a bunch of correlated things are allowed to not be orthogonal.
Yeah. Are certain novel deep learning model architectures, such as graph neural networks, particularly amenable for interpretability or post hoc explanations?
I'm not sure. I think that there are some really nice works in creating neural architectures that force kind of if-then logic, if-then reasoning. And those are actually really cool. They've been able to, I don't work on that, but they've been able to show that that if you force like a decision tree in the top few layers, that you can actually see kind of this if-then logic kind of propagating in the last few layers. Like I said, I think it really just depends on the domain that you're using these things for, whether it's actually interpretable. So without an actual domain, it's hard for me to answer the question.
Yeah. So in your concept whitening paper, which I've read, you point out that concept whitening doesn't necessarily make CNNs entirely interpretable. They allow us to see the network and how it's processing information. Other forms of deep learning are currently similarly limited. You gave some examples in that paper as well. Do you see deep learning as permanently, or at least in the near future, constrained to basic forms of interpretability rather than a full understanding of the computational steps in favor of flexibility? And if so, is this a disadvantage of deep learning for high stakes decision making?
Yeah, I mean, I think that if we actually understood how to make these things interpretable, we could potentially do it. But I think just sort of figuring out what the right definition of interpretability is tricky enough that it's been stopping us.
Yeah.
So I do think that for high stakes decisions, deep learning is mostly not really going to cut it right now. There are a couple of exceptions. So there's been some work on things like segmenting chambers of the heart with machine learning, where all you're trying to do is make a doctor's work faster. So
Mhm.
let's say the doctor has to segment the chambers of the heart. Well, it sent it into the machine learning algorithm. It does a preliminary segmentation and the doctor fixes it. Right. So in that case, you can use whatever algorithm you want, whether it's a black box. It's fine if it's a black box because the human can check it and fix it afterward.
Mhm.
And there's a bunch of other things like that. Like I think for maybe breast lesion detection in mammograms,
Yeah.
if there is no lesion, if there's literally no lesion in the tissue at all, that
Yeah.
might be something a neural network could do as a black box, because the explanation is simply there exists no lesion in this breast.
Yeah.
So things like that.
Yeah. So you're touching on another topic here, which is similar to another question. And I think you mentioned this a bit in your paper on interpretable models. Who decides what counts as interpretable? And I think in your paper, you sort of hinted that it should mainly be domain experts, right? And does the interpretability of algorithms also depend on the questions you're asking and the goal of your analyses?
Definitely, of course. Yeah, it depends on it's like the whole data science process. Interpretability is part of that process. And so you have to consider its full cycle in how it's deployed. Like you might use a different type of interpretability for an analyst troubleshooting the thing than the loan officer who's making decisions, than the loan applicant who just needs, some kind of explanation that might be different from the loan officer. Yeah.
Yeah. So why are people so caught up in non-interpretable models or black box models if they're not more accurate? Is it just a trend? Are we lazy? What's going on here?
I'm not sure. I think differently than other people. And so for me, this is all obvious, but a few years ago, after people started using Lime on everything, and I realized they were calling these approximations explanations, and then everybody was saying Lime didn't work. And then I was like, why are we doing this? This is so stupid. None of this makes any sense. And that's why I had to write that paper. I think people love the idea of, and by the way, a few years ago when I wrote that paper, people would walk up to me and start screaming at me. Like I'd give a talk and people would come up after me and start screaming at me. Like, wow. What's wrong with this I like my black box. Like there's nothing wrong with the black box, and it's like, well, maybe for your application there isn't, that's fine. But I'm talking about high stakes decisions here. And these are decisions that heavily affect people's lives. And we need to be able to check them. Yeah. So yeah, I was really surprised at that pushback. And I think the reason is because people love the idea of something capturing some gold piece of knowledge that a human can't understand. Like it's a puzzle or some mysterious pattern that a human's not capable of understanding. But yeah, that's not really realistic. It's just their fantasy of what they'd like.
Yeah, sort of like a science fiction novel. So on the point about explainability versus interpretability, how useful would interpretable models be for people making high stakes decisions with no domain expertise in machine learning?
So that would be a really bad idea.
Yeah.
For high stakes decisions, you have a human decision maker. Like for a doctor, they know that domain and they should look at the model's results and decide whether or not they want to trust it. Yeah. They shouldn't just blindly trust it. They should decide whether it's making a good decision here. They should look at it and say, oh, there's a typo there. Or, oh, I don't think I trust this model. It doesn't really work for patients like this. Or this model is operating out of the domain that it was trained in. I don't think I want to trust it.
Yeah. So are there any legal implications to a model being interpretable versus black box, such as in healthcare and software medical device contexts, but any other field? Are there any legal implications for being able to understand a model and interpret a model versus the black box models?
There are responsibility issues. Like if the model predicts something incorrectly and the doctor can't understand the model and they just follow what the model says, well, whose fault is it? Who do you sue? Do you sue the doctor for trusting the black box, or do you sue the designer of the black box?
Yeah.
not really clear because, you know, these black boxes, they really compromise the doctor's ability to make a decision jointly with the patient and with the data.
Yeah.
Yeah, so there's those issues. There are other legal issues as well. There are many legal issues. I'm not a legal expert, so I can't really comment on all of them, but we ran into one the other day. We're writing a paper on embryo selection in vitro fertilization. And we ran into an interesting issue where, let's say somebody does a randomized control trial, right?
Mm-hmm.
With a black box model, and something bad happens, right?
Yeah.
And who's responsible? Because, you know, you did this RCT with this black box when maybe you could have done it with an interpretable model and knew that something bad would happen.
Yeah.
You know, who's then responsible for this? Yeah.
Yeah. So keeping in mind that you're not an expert in law, in your experience currently, do you think the existing data usage laws encourage the development of more interpretable models? Are there incentives for developing interpretable algorithms, such as predicting credit scores, and then being able to provide reasoning for the increase and decrease of an individual's credit score?
So the laws right now favor black boxes with explanations. Because even the laws that say, like the GDPR or something, even the laws that say that you have a right to explanation, it's just an explanation. It doesn't even matter if the explanation is crappy. It can be an explanation. And even something like Compass, there's been lawsuits where it upheld the use of these black box models for high stakes decisions. It upheld the use of proprietary models because it wants people to develop them.
Yeah.
So, you know, I think there should be a regulation that if you're going to use a black box model for a high stakes decision, you really should prove that there's no interpretable model with the same level of accuracy. I think would be a funny challenge, because of course they would never be able to prove such a thing, because you can always find an interpretable model and these machine learning problems. So I think that would be a really neat regulation.
Yeah.
But yeah, it's a little bit more than I hope. For loan decisions, that's heavily regulated. And the models have to be interpretable, but you don't get to see them.
Yeah.
You don't get to see them. And I know that those models don't make any sense, because I paid off a loan recently and my credit score went down. Looking at this going, what in the world? How is it possible? And then I Googled it, and it turns out this is a standard thing.
Yeah.
Like, you owe money to a lot of people, your credit score goes down. And I was like, but I just paid off the loan, so it should go up. And it just shows you that these models actually do things that are unintuitive, and that they're not really properly designed, despite all of the massive effort that goes into that.
Yeah. So speaking of banks and loans, how do you think about promoting or facilitating the application of your research in industry? Do you have tips for practicing data scientists for applying your research? Do any of the techniques developed by your lab have implementations especially ready for use in the industry?
Yeah, so we have a model that's in use in Massachusetts General Hospital for predicting seizures in critically ill patients that are in the intensive care unit, being monitored for, they're being monitored for brain seizures with continuous EEG monitors. And that model is, you know, according to our collaborators, it's helping save lives and preventing brain damage. So you know, some of it is in use. And we have code for all of our papers that have some methodological component. We built software packages for those that we would love it if you give it a try. And if you run into any trouble, you can always email us too. We're pretty good about answering email and trying to help you implement it and getting troubleshooting it.
So somebody else said, your talk makes me wonder, with more and more organizations using data analysis to make decisions, whether you're concerned or whether you see that the inherent bias in algorithms is getting worse.
I don't know if it's getting worse. I don't have a perspective that is overarching enough to be able to know whether bias is getting worse. You know, in fact, you should think about comparing with the status quo, which is humans making decisions. So for instance, there's been a really big pushback on algorithms in criminal justice, helping judges. But the problem is that what's the alternative? It's a judge making decisions. Judges are racially biased. Judges can't process whole databases of data in their heads. They can't calculate probabilities of recidivism. And so, you know, it's much easier to fix a biased algorithm than it is to fix a biased human.
Yeah.
And so, yeah, I think when you're asking these kinds of questions, you want to think about how it compares. Is it improved? Is it at least improving over what we have now?
Mm-hmm. So a couple more questions. With the pending deconstruction of the for-profit prison system, do you anticipate it being possible to leverage new interpretable models to help the formerly incarcerated populations reintegrate?
I hope so. Unfortunately, despite the huge amount of work in reentry programs, how do I say this? I don't want to say it without hurting someone's feelings or whatever. It hasn't been proven that these reentry programs actually work. And it's terrible because the reentry programs are the key to getting people reintegrated in society. And I sort of want these programs to work with all my heart. So I think even just proving whether the reentry programs are effective is going to be hard enough. You know what I mean? Like you need to know that the reentry program is going to be effective for a person to know the predictive model should lead you to place them in that program. Yeah. It's very hard to do that kind of causal inference study on these reentry programs.
So I think I'll end on this question because I actually peeked at your slides and know you have some information on this. What do you think of variable importance as an approach to interpreting black box models, refitting the model once for each variable, each time with the variable permuted, and see how the model accuracy changes? It seems like such an approach would have been useful in ProPublica's analysis of race in the COMPAS model. Can such approaches get us halfway to interpretability?
Yeah, I think so. You know, we did do some variable importance analysis on COMPAS, even though we don't have access to the model. We made some pretty mild assumptions. This is work with Francesca, by the way. We made some pretty mild assumptions that allowed us to try to get at what the variable importance of race to COMPAS might actually be. So without knowing what COMPAS is, we could still calculate a range of how much it might depend on race. And that range starts from 0 at the bottom, which, you know, to be honest, we actually don't think COMPAS depends on race other than through age and criminal history. But it does go fairly high up because of the correlations of these variables. It's possible that it is possible that COMPAS does depend on race, in addition to age and criminal history, and we kind of quantified that. Yeah, without knowing how much COMPAS, without knowing exactly what COMPAS's formula is, we made a kind of an assumption on what its model form might be, and use that to get our bounds.
Yeah. Well, thank you so much, Cynthia, for an excellent discussion and being so genial with answering the questions. David?
Thank you so much, Cynthia, for such a wonderful talk and discussion. And thank you, Hannah, for your moderation. Cynthia, you can probably see we had way more questions than we could possibly get to. There are 20 or 30 more questions that are unanswered. This is so important. I want to underscore what Cynthia said, this need to make better decisions than decisions that people make in high stakes settings, but without making new mistakes or introducing new biases. I think that is exactly what both the opportunity and the challenge is here. We're having a very active debate. We're so fortunate, Cynthia, that you could join us. You're leading the community to think through all of this, both through your scholarship and for your wonderful outreach and presentations and talks like the one that we just heard. For everybody in the audience, just to know, next up, February the 25th, Rashida Richardson will be giving the next of our seminars in our Bias Squared series. Rashida is a lawyer with Rutgers Law School, and she's also associated with the AI Now Institute at NYU. She's a lawyer and a researcher interested in the social and legal implications of big data and data-driven technologies with a racial justice emphasis. Again, thank you to all of you out there in the audience as well for your engagement and asking questions. And thank you to Cynthia Rudin for joining us. Hope you all have a great afternoon. Bye.